Linear relations. So first of all, what word do you see in the word linear? Line. Excellent. I'm so glad none of you said ear. There we go. Some clown always says ear. Right. Okay. Anyways. Yeah, but near isn't funny. Ear is funny. Well, they think ear is funny, but it's not. So anyway, you see there's a line in it. So a linear relation is going to make a line. But the problem with that, you'll see in a moment. So, Pizza Hut is making pizzas. They charge $12 for an extra large cheese pizza. Each topping is $1.50 extra. Now, some clown kid always says here as well, cheese is a topping. No, it's not. Without cheese, you have bread. No. Tomato sauce is just like spreading butter on toast. You need cheese to make it a pizza. So it is not a topping. So, if we were going to graph this, we need to decide on a few things. What do we need to decide on? Somebody go. Domain and range? Yeah, but before you can decide on the domain and range, what else do you got to decide on? The variables. What's independent? What's dependent?
Time is independent.
Dude, we're making pizza. There is no time here.
Number of pizzas.
Number of pizzas?
Cost is the same.
Cost and toppings.
So cost and toppings are the two variables, right? They're the two things that can change. Cost and toppings. Which one is the IV? Which one is the DV? Emma. IV is the cost?
Yes, but no.
Toppings is independent. Why?
Cost depends on
Cost depends on how many toppings you have to order, right? Kids have a lot of trouble with independent and dependent variable. I don't know how else to explain it. If you order more toppings, you pay more money. So cost depends upon the toppings. So down here we're going to have the toppings. 1, 2, 3, 4. And I'm going to stop there because anything more than 4 toppings on a pizza is disgusting. And one of those toppings cannot be pineapple. So, no, shut it. And here's something interesting that a lot of people do not know. The Hawaiian pizza, ham and pineapple, is a Canadian invention. Yes. Along with the zipper. Along with basketball. No, hockey is pretty strongly debated. Yes, the goalie mask was invented by a Canadian goalie because he was tired of getting pucks in the face. I don't blame him. I play goal. A puck in the face when you're wearing a goalie mask still hurts. Anyways, so what is going up the side here? What's going up the vertical one? Cost. Excellent. What do we measure cost in? Dollars. Unless we're in Europe when we do it in euros. Or in Korea where we do it in won. But we've done that gag already. So I'm not going to do it again. Huh? No, there are no francs anymore. There's no francs anymore. No, there's not. Who uses francs?
Madagascar, Gabon, Luxembourg.
Luxembourg doesn't use francs. They use euros. But Madagascar might use francs. Actually, I always forget about how many African countries are still Frenchy. You're right. Congo probably uses francs too. I bet they do. Spend a lot of time in the Congo, Emma? Oh, yeah? They still use francs? Yeah, because they were French. Rwanda probably uses francs as well because they speak a lot of French in Rwanda. Because of the horrible policy of European countries taking empires. Because why wouldn't you? All right. So, what's this first number going to be? 12. Excellent. And then what's the next number going to be? 13.50, because I go up by $1.50. What's the next number going to be? 15. What's the next number going to be? 16.50. Excellent. So, if I order no pizza, how much would I pay? Zero money. Do I need to put a dot there? No, okay. If I order a pizza with 0 toppings, how much do I pay? $12. Excellent. I didn't fool anybody. Grr. That makes me angry. I don't like it when I don't fool you people. If I order 1 pizza with 1 topping, how much do I pay? $13.50. 2? $15. 3? $16.50. 4? $18. Everyone agree? That is what my graph should look like, yes? All right, now let's talk about yesterday before we go on. Yesterday we talked about discrete and continuous data, yes? Is this discrete or continuous data? I got 2 people saying continuous, 2 people saying discrete. What is it? It is discrete. Why? You are counting the toppings, right? Can you order half a topping? No, you can order toppings on half a pizza, but you can't order half a topping, can you? So if I want half a topping, which would be an input of 0.5, do I get an output? No. So this is discrete. Everybody cool? So it's discrete, but, and this messes kids up, even though it's discrete, and since it's discrete, we don't connect the dots, connect the points. Now, without connecting the points, there's no line, is there? Right? But even though it's discrete, it's still linear. And this bugs kids because they don't see a line. So they're like, how can it be linear? What makes it linear is this. And I'll use yellow to graph that. What makes this linear is it has a constant, can you see that yellow on the right? Constant rate of change. What do you mean it's got a constant rate of change? When I go 1 topping on the IV, I go 1.5 on the DV. Every time. That is what makes a linear relation. Does everybody understand? It's not whether or not it has a line. It's whether or not the rate of change is always the same and predictable. Everybody cool? Everybody understand? Okay, so before we go on, just let me remind you, remember when we did the car rental? Is that a linear relation? The rate of change was always the same? Was it? For the first 3 days, it was 1 and up 65, right? Then what happened? Started going up by 30. So is that linear? No, because the rate of change is not always the same. Does everybody understand? Yeah? Okay. So this right here, this is one way to describe a linear relation in words. What's the second way to describe a linear relation? What did we just make? We never drew a line. What did we just make? A graph. That's the second way. The third way is a table of values. Now, table of values is what I called it when I was your age. But for some strange reason, the term table of values has become very unsexy. And all of you call a table of values a T-chart because it looks like a T. I hate that. It's a table of values. And all tables of values work the same way. On this side is the IV. On this side is the DV. No matter what. Everybody understand? So, if my IV is 0, what's my DV in this case? 12. If my IV is 1, what's my DV? 1350. My IV is 2, my DV is 15, right? My IV is 3, my DV is 1650. So that's the third way to do it. And the fourth way to do it is an equation. And an equation can be gotten in two ways. We can get the equation from the graph, or we can get the equation from the table. We're going to do the graph next unit. We're going to do table right now. All right? And here's how you do it. Some of you will have seen this already before. Some of you won't. How much did this go up by? 1. How much did this go up by? 1.50, 150. 1, 1.50, 1, 1.50. Is the change the same all the way down? So we know it's a linear relation, right? So how do we get an equation out of that? Well, every equation is always the dependent variable, because the dependent variable is the result of doing math, right? The dependent variable, it's always the IV and some math. I made that too close. Always. Every equation, the dV is by itself, and then we do some math to the IV. All right? So in this case, our dV was what? Cost. And our IV was what? Toppings, which I'm going to use T and C, yeah? Okay, so our cost is our dV. So let's have a look at this. When it's 0, 12. Easy. No math happening, right? All right. Now, to get the 1350, I added 150, yes? But what really happened is I had 12, right? And I added $1.50, yes? Everyone agrees? Well, when I go to 2 toppings, do I still pay that original 12? Yes or no? Yes. And do I still pay $1.50? But how many times do I pay $1.50 now? 2 times. Agreed? What happens here? 12 plus $1.50 times 3, right? Everyone agree? What's the next one going to be? 12 plus times 4, right? What's it going to be if I do T toppings? Something has just happened in math 3 times. What is it going to be, Addison?
12 plus 150, T,
Done. Is that my independent variable plus math? There's my independent variable, T, and there's the math, yes? 112 plus 1.5 T. And now, because that's linear, this is going to work forever, isn't it? If I want 6 toppings, how much is this pizza going to cost me? Why? It's another $1.50. So cost is going to be 12 plus 1.5 times 6. 1.5 times 6 is 9. 9 plus 12 is? He waited patiently. 9 plus 12? 21. So our cost is $21. Everybody cool? What if I have $30 to spend? How many toppings can I get? I'm getting 1 pizza. How many toppings can I get? I have $30. Where does the 30 go? At C or at T? C. 30 equals 12 plus 1.5 T. How do I find out how many toppings I can get? What do I have to do? Amelia. Minus 12 from both sides 18 equals 1.5t. Then what? Divide by 1.5 and t equals. He waited patiently for one of the class who gets their calculator to do 7 plus 2 to do 18 divided by 1.5. 12. 12 toppings on a pizza is disgusting, but some of you might actually like that. I do not. I have tried many places that have an all but the cook pizza special or everything pizza special, and they are disgusting. All it does is taste like mush. What?
What's your favorite kind of pizza?
Depends on what kind of mood I'm in. I am a big fan of pepperoni, bacon, mushrooms, and hot peppers. Either banana or jalapeno. I am also, however, a big fan of tomatoes, spinach, feta, and chicken. But I'm also a big fan of just the plain old margarita pizza, which is just tomatoes, cheese, and basil. Like that too. Hate seafood on a pizza.
Have you tried club chicken pizza?
No.
It's like pizza with Alfredo sauce instead of tomato sauce.
Yeah, I'll accept an Alfredo sauce sometimes. What?
Have you tried Pizza Garden?
No.
It's like it's kind of like a new place here. Where Ken's Farm used to.
Yeah, but if they don't have gluten-free crust, I can't eat it.
I think they do. They're like a health place.
Well, maybe. I'll have to check it out. Yeah, I know where Pizza Garden is. It's where Flying Wedge used to be over by Shoppers Drug Mart. Yeah, that was Flying Wedge pizza back in the day, which was delicious pizza. All right, so linear relations come in 4 types. What are they? Or 4 incarnations. What are the 4 ways we can have a linear equation? What's number 1? Words. What's number 2? Graph. What's number 3? Table of values. What's number 4? Equation. And all of them are exactly the same, right? You can take, if you have any one of those 4, you can make all the other 3. Everybody understand? Right? Okay. Let's see if we can indeed. What do I have here? Table of values or words or graph? I have a T-chart. A T-chart is actually what's on the wall at David's T because it's a chart of T's. This is a table of values. Is it linear? Let's check. How much did I go up by there? 5. How much did I go up by there? 9. How much did I go up by there? 5. How much did I go up by there? How much did I go up by there? How much did I go up by there? Is it linear? Yes. Why must I do 3 points? No kid gets this question right. Why can I not stop right there? Why do I need that 3rd point? Why can't I stop there?
Because you need at least 3 points to make a pattern.
Yes. 2 points. The 3rd one could be anywhere, couldn't it? Right? You need 3 before you have a line.
On the first kid, you get that right.
Yeah.
Yay!
Go have a gummy bear. On me. Yeah. You can't. This is a gift gummy bear. It's offered once and once only. If you get rid of this pop-up, you're never getting it again.
What if you're a virus?
Huh?
What if you're a virus?
Maybe I am. It's a risk he's got to take, like you have to take with every pop-up. That's what I'm saying. But enough idiots click on the pop-ups that they keep continuing to exist, don't they? Right? How many times have you been told you're the millionth customer of something and you've just won a car? Yeah, you ever click? Somebody does. All right, let's do the next one. What'd I go up by? 5. What'd I go up by? 75. You can already see. What's this one going to be? 2,925. Is that linear? No. All right. So now we've got an equation. Is that one linear? How do you check? You can't solve it. There's two variables. Amelia. As long you have two choices. You could make a t-chart or a table of values, or you could just substitute points, yes? Which of these is the easier point to substitute? X or Y? X, of course, because X is where all the math is, yes? If you say any number for X, can you tell me what Y is? Yes, because X is the independent variable, right? Say three numbers.
1, 2, 3.
1, 2, 3. When X is 1, what's Y?
6.
6. When X is 2, what's Y? 8. When X is 3, what's Y? 10. Linear? Yes, because it went up by 1 and up by 2. So that's linear. What about this one? Same thing, right? Let's use 1, 2, 3. When X is 1, what's Y? 3. When X is 2, what's Y? No. No. 15. Right. When X is 3, what's Y?
35.
You sure? Yeah, it is. Is that linear? No. So real quick and easy. Something just happened once in math. What's the difference between those two equations? What's the easiest thing you can see that is a difference between them? Jacqueline? Yeah, when we do this, linear's got the pattern, but I'm talking only the equations. What's the difference? Right, not a square root. A square. And exponent automatically makes us nonlinear. If there's no exponent, it's linear. Okay? All right, let's look at the next one. Linear or nonlinear? Why? So you're 50-50 in it. Okay? Why?
Because I just see that in like the box that it's touching here, it's in like the bottom side, and in the box that it's touching over here, it's the top side and the bottom over here. And I just don't think that's linear. I think the other one's linear because it's straight across.
Well, we'll get to E in a minute. Don't give me away. Amelia.
Because when you go from the top to express to the right and then to the bottom, and along on the end of the graph, it's the same, you just can't see it.
All right, well, let's have a look. There's a point we can all agree on, yes? 1, 1, yeah? Okay. So if it's linear, it's going to make a pattern, yeah? So if I go up 1, I go over, what is that, about 2/3? Everyone agree? Okay, if I go down 1, do I go over the same amount? So is it linear? Yes. Way to go! Braden's new nickname is 50%, not 50 cent, 50%. What happens when I ask you a question with 3 choices, Braden? Addison, you say that's linear. Why? And don't say because it makes a line. Because this one made a line, you said it wasn't linear.
Because it's going straight across.
Okay. So if I start there, and I go across to there, and then I go across to there, is the change the same? Yeah, because I'm not going up at all. I'm just going across, right? So that one is linear as well. Turn the page over. What about 101? What about F? No, of course not. Just by looking, right? Why? It's a curve. When I go from 1 out to 1, I went over 1 and down 1, didn't I? But at the next one, I go over 1, and I got to go all the way down here. So that's nonlinear, which I've been writing in red. Oh, I've used pink there, but that's okay. And what about that one? That is linear. Everybody cool? All right, now, the very next unit you can see is all graphing. You can also see we're approaching the end of this unit, so it's time to start introducing graphing, yes? All right, you all did this last year. I even tell you what to do. Make a table of values and graph. Why have I used X and Y instead of IV and DV?
Because you don't know what like this.
What's the question have? Question has X and Y. Okay. Which numbers am I allowed to choose? X's or Y's? Why am I allowed to choose X's? Because it's the side with the math. It's the independent variable, right? No matter what I say for X, we can easily find Y, yes? Now, what would be 3 smart choices? 1, 2, and 3 would be fine. Give me another 3. 2, 4, 6. 0, 1, 2. 5, 10, 15. 10, 20. As long as we keep a pattern, it will be a good choice, yes? But I notice not one of you said a negative number. Doesn't a linear relation go in both directions? So shouldn't we have a negative or two? You should. But it's not necessary. Because often are negative numbers part of a real life linear equation? No, of course not. 'Cause we can't have negative costs and negative toppings, can we? So even if we only use positives, once we prove it to be linear, could we not just add the negative numbers? Because we now know the pattern? So let's use 1, 2, and 3. That sounds cool to me. Why, this is my graph paper. Could I use 10, 20, and 30 if I wanted to? How could I use 10, 20, and 30 if I wanted to? I would have to make these 10s instead of 1, 2, 3, right? It would be pointless because it would be the exact same result, wouldn't it? Okay, so if I use 1, what are my Y values? 6, 8, 10. So let's put that on the graph. 1, 1, 2, 3, 4, 5, 6. 2, 8, 3. Oh, I'm going to go off the graph. So what can I do? Because I need 3 points, don't I? Well, couldn't I just go down 2 and over 1? Because we know the pattern now, don't we? For every 1, I'm going to go up 2. So down 2, over 1, down 2, over 1. How long could I keep making these dots? Till I run out of graph, if I wanted to. Do I need to? No, because it's a pattern, right? Once I have 3, what can I do? Once I have 3 dots, what can I do? Okay, and then what would I do? Is this continuous or discrete data? It's continuous. Of course it's continuous. Can I put any number in for x, including a fraction? Will that give me an output? So is it continuous? So I can draw the line. Yeah? Now, let's do the next one. First of all, by looking at the next one, is it going to make a straight line? How do you know? It's got an exponent. Now, remember we made a mistake with this one because we chose no negatives. We went off the graph, yeah? Should we choose a couple of negatives this time? Let's go -2, -1, 0, 1, 2. What happens if I put -2 in for x? What do I get? This way I get to test your exponent abilities as well. What do I get? 1. Thank you. -2 squared is 4. 4 minus 3 is 1. What if I put -1 in? Negative 2. What if I put 0? Negative 3. What if I put 1? Negative 2. What? What if I put 2? Look again. 1. What? Let's do the graph, shall we? Negative 2, positive 1. Okay, there's a dot, no problem. Negative 1, negative 2. Okay, there's a dot, no problem. 0, negative 3. There's a dot, no problem. And it makes the fancy curve, which we call a parabola, which you don't have to care about until next year. We already knew it was going to make a curve, though, didn't we? Why? Because it had the exponent, right? Now, when it's a squared exponent, obviously I have to go down and back up, don't I? Because when you square a negative, what do you get? A positive. What do you think would happen if I cubed it? What do you think the graph would look like? Can you still have negatives? You can, can't you? So what do you think the graph would look like if I cubed it? Just out of curiosity.
It would be like not just like one slope, it would be multiple slopes.
What do you mean?
Like you made the one slope that's a U shape, it would make kind of like a bell shape.
So you think it would look like this?
Yeah.
Okay, that's a good guess. Any other guesses? Addison?
Like kind of like multiple, like this, like a star.
Like that? Okay. Any other guesses?
Might it be more drastically curved?
More drastically curved? So like instead of being spreading out so far, it would go up faster? No, it's going to have an exponent, so it can't be linear. You're right, Jacqueline. It's going to go up way faster, right? Because instead of being 1 squared, or instead of being 2 squared, it's 2 cubed. So it's not 4, it's 8. So it's going to go up way faster. But are we allowed negatives? What's negative 2 cubed? Negative 8. So at 0, it's going to reverse. It would look like this. Kind of like a parabola, but the second part flips downwards because negatives would stay negative. Everybody cool? You don't got to worry about them till grade 12. I just wanted to show them to you. Don't worry. Hey, Jaden, eventually you're going to do a graph that looks like this. You ready? It's got dotted lines. And the graph lives like this. That's coming for you. That's called a hyperbola. Not hyperbole, hyperbola.
How would you do like the table of values for that?
The table of values for that is really weird. What happens with that is there's numbers on the bottom, right? So like if I had x, 1, 2, 3, 4, 5, 6, x plus 6 on the bottom, you couldn't ever have x being negative 6, could you? Because then you'd have negative 6 plus 6, which would be 0, right? So that's why this line is here. X can never hit that line. Well, because if x is ever 6, you're dividing by 0, and that's impossible. You understand? And then over here, 1, 2, 3, 4, 5, 6, 7, 8. Somewhere else in the equation, I have x minus 8. Because if x hits 8, 8 minus 8 is 0, so I can't have that. And somewhere, I have 1, 2, 3, 4. Y plus 4. Because y can never hit negative 4, because negative 4 plus 4 would be 0. And then there's other stuff up top. And then you got to get that on a graph. Huh? Doesn't look like... That's not a table of values. That's the equation that you would be graphing. It would be equals, plus, and there would be different stuff up top. You wouldn't need it at all. I've explained this already. Once we started factoring, for the bulk of grade 10, most of it is not needed for life. It's needed for future math. Many of you aren't going to do any future math, but some of you might. I taught a kid in grade 9 once who said math was his least favorite subject. He hated it. By the time he got to grade 12, he left here and went off to university to become a mathematician. I know, weird, hey? Same kid that bought me this microphone, actually. He was in my class for grade 9, 10, and 11. And then he went to Mr. DeVries' class. He's like, math is awesome. I love it. And I was like, yeah, I remember 4 years ago. Yeah. All right, we are done. It is 9:24. Please do page 308. Again, it looks gigantic because of all the pictures. And again, do you need to do it all? No, but if you're going to give up or say, I don't need to do it all, you better be able to do the last few, like 14, 15, and 17 type of thing. Aight? Aight. And what should we have had today, but I didn't give it to you because I don't believe in pop ones? What are we going to have tomorrow? A quiz. I'm not going to give you a quiz on the day after Halloween because, of course, you'll all be out lighting firecrackers and eating candy. Because I was a teenager, scant 20 years ago, 30 years ago.
Were you?
Man, my wife and I were just talking about that today. Neither one of us has any problems with getting old until you start doing the math. It's been 26 years since I was a teenager. Yeah, I know, right? I don't care that it's been 26 years, but you forget how old you are until you start doing math. Like even for you guys, honestly, it's been 12 years since you were in a diaper. That's long. In 12 years from now, you guys will be 26. Some of you will be married with children. Some of you will still be living in your parents' basement.